Lesson 8, Oxidation Chemistry, is another one of the hard chapters. It only has one kind of problem that's hard. So email me if you get stuck. But if you remember how to balance equations, and if you do a good job paying attention to the chapter, it's tricky, but it's doable. And I have to admit, they're actually my favorite problem of all the different kinds of chemistry problems that we do. And I think for me, it's because I feel like I've solved a puzzle when I've solved this problem, because I don't know what the answer is going to be until I get to the end. So when you do your redox reactions, which you've already learned about, by the way, in the first section of chemistry, they just didn't talk about it. When you're talking about types of chemical reactions, single replacement, decomposition, combustion, and synthesis reactions are all redox reactions. So if you remember when we talked about whether or not a reaction would occur and about the activity series, then you've got a good basis for this chapter. So it's really not too bad except for the one hard type of problem. And the hard type of problems is balancing redox reactions by the half reaction method. So there's lots of help out there on the internet if you want to watch some extra videos. But the book gives you some good examples, and I've worked out some for you as you go through the modules. But I just kind of wanted to show you an example of a simple one and an example of a hard one. Both of these are I don't remember which question it was, but it's out of the back of your chapter. And it says balance these redox reactions. Now, I haven't balanced them for you, but I just wanted you to see, if you look at the black handwriting, it's just a simple equation that we've balanced. This is just a synthesis reaction, right? Aluminum solid plus chlorine gas reacts to form aluminum chloride. Pretty simple. You can balance this just by looking at it, by adding a couple 2s and 3s in there, and that's an ALS. Sorry, not an AL5. Okay, now here's where it gets weird. Look at the numbers on top. These are oxidation numbers. They don't really exist. Because of the way that the electrons are shared, sometimes molecules will act like they have a charge, or if we give them this charge, they'll help make more sense. So that's all oxidation numbers are. They're not real. And there's rules for oxidation numbers, and they're very clear in your book, so write down those rules and learn them. One of the rules is if you have an element in its natural state by itself, then the oxidation number is 0. So aluminum is 0, chlorine is 0, both on the reactant side. And then if you have an ionic compound, the ionic charges are the oxidation numbers. So chlorine's -1, aluminum ion is +3, no surprises there. Look at the brackets that I made. When we talk about redox reactions, something is reduced and something is oxidized. And we can tell what's reduced by looking at how the number changes. So chlorine goes from a 0 to a -1. Its number went down. Reduction. Pretty easy to remember. So I just write red, negative however many it went down, and I tie the two together to remind me which elements they are. And then oxidation, the number goes up. So aluminum went from a 0 to a +3. That's the element that's oxidized. When you balance by the half reaction method, you then break it down into its half reactions. So the half reaction for for aluminum is Al yields Al3 plus. Oh, but you know what? At the beginning of chemistry, you learned about the law of conservation of matter. There's also a law of conservation of charge. And in this chapter, we have to make sure our charges are balanced. So look, aluminum is neutral as a reactant. The product side must also be neutral. How can I balance charges? Add electrons. -3 plus +3, neutral. Now my product side is neutral. It happens the same way on the reduction side. Cl2 plus 3 electrons, the reactants equal -3 on the charge. The product is 3Cl negative. So the product is also 3 negative. -3 reactant, -3 product. And in fact, reduction is gaining electrons. So electrons on the reactant side is good. But it wasn't balanced. So 3Cl2 plus 6 electrons yields 6Cl negative, and that way they're both balanced with a negative 6 charge. Now the reason I wanted to show you an easy one is because these get really tricky. This is about as hard as they get, and I'm not even exactly sure that I have it balanced correctly. But once again, we have Cl2 plus KOH yields KClO3 plus KCl plus H2O, the black. You might be able to balance that just by looking, but I guess it would be tricky. And then you have to make sure your charges stay balanced as well. In this case, everything's neutral, so that probably whatever you get is going to be the correct answer. But here's the weird thing. This will sometimes happen. The chlorine is both oxidized and reduced. So some of these molecules react so that they lose electrons, and oxidation is loss. Notice on the red oxide or the blue oxide oxidation reaction, we're losing electrons. Reduction is gain. We're gaining electrons. So when you break these down into their half reactions, you got a lot of things to think about. So in this case, because your potassium hydroxide and your potassium chlorate and your potassium chloride are ionic, something that you can do is you can actually break them down into their ions, because they're spectator ions, if you remember your solubility equations, and net ionic reactions. So you might go back and study those as well. That can help. So I like this chapter because it's so complicated, but I know that that's probably not how most of you feel. Take your time. It's doable. It follows the rules of chemistry you already know, and there's not a lot of math. In this case, we're balancing equations, which is a different kind of math, but you can do it. Email me anytime. Do a good job with this section, because we're going to talk about oxidation and reduction again in the next chapter. Bye.